In the previous video, we talked about psychology as a science. That means that psychologists collect empirical, or observable, measurable data and analyze it in an objective way. In the next few videos, we'll explore a little bit more what this process looks like. First, let's talk generally about the process of descriptive and inferential statistics. Don't worry, I'm not going to ask you to do any math. But it's important that we understand conceptually how researchers use statistics in order to interpret the empirical data that they collect. When we collect data from a sample, we might first be interested in describing what that sample is like. That's the job of descriptive statistics. For example, we might be interested in the gender or ethnic breakdown in our sample, or participants' average self-esteem scores. We are also often interested not just in an average tendency on a particular variable, but also in the distribution of scores on that variable, or how many times each score occurred in our sample. It turns out that for many variables, scores will often tend to be distributed like the graph shown in this picture. Because this distribution is so common, we often call this a normal curve or a normal distribution, or you may have also heard it referred to as a bell curve because of its shape. Let's imagine for a moment that this is the distribution of scores in a sample for the variable height. Take a moment now and examine the normal curve. What do you think it's saying about the distribution of height scores in our sample? Essentially, when variables are normally distributed, as in this graph, it means that most people are average. In fact, almost 70% of the sample, 68.2% to be exact, score fairly close to the average or mean, as you can see in the two darkest shaded bars. In contrast, very few people score at either extreme. You've probably experienced this yourself. Although you may know some people who are very short or very tall, most people you know are probably close to the average height for their gender. Again though, it turns out that it's not just height. Many other variables such as IQ, extroversion, self-esteem, you name it, usually fall on a normal curve that looks something like this. This is important because many of the statistical tests that we run have as an underlying assumption that scores are normally distributed. So what happens if this is not the case? We call this skew, and it can happen from time to time. Data that are negatively skewed look like the graph on the far left. Most of the scores are clustered near the higher end of the variable, with fewer low scores. In many college classes today, exam scores tend to be somewhat negatively skewed, with most students doing generally pretty well and fewer students obtaining extreme low scores. Data can also be positively skewed, as in the graph on the far right, when most of the scores are clustered near the bottom of the distribution. In many college samples, scores on a test of severe mental illness would likely be positively skewed, with most students exhibiting relatively low levels of symptomology and fewer students with higher, more extreme scores. I mentioned earlier that many statistical tests have as an underlying assumption that the data are normally distributed. So can we still work with skewed data? It turns out we can, as there are actually some ways to mathematically transform a skewed data set into one that is more normally distributed. The most common way to do this is through a logarithmic transformation, where scores are transformed from their original units to log units. Although understanding the distribution of scores in our sample is important, most often that's not what we primarily care about. Most often, researchers are primarily interested in making a more general claim about the broader population. For example, let's say that we're interested in the potential relationship between sleep and GPA in college students, and we collect a sample of 200 students to be in our study. While the data from the 200 sample participants is certainly interesting, what we really want is to be able to make a claim about all college students more broadly, not just the 200 people that were in our study. This is where the process of inferential statistics comes in. If we could collect data from every single person on the planet for all time, we actually wouldn't need statistics. We could just look and see if there was a relationship. However, because we're limited by, practical reality, instead, researchers must rely on collecting data from samples and inferring, based on that sample, what is likely true about the population of interest. Election pollsters do this all the time. They might sample from a smaller group of people and then try to infer, based on their sample, how the entire population will likely vote. As you might be aware, there have been a few cases of pollsters calling an election incorrectly, most recently in the 2016 election. This is because the process of inferential statistics is not perfect, and in order to infer from the sample back to the population, we must first make sure that our sample looks like or is representative of our population in the first place. Scientists can do this through a process called probability sampling. However, although the inferences we make based on samples are not always perfect, more often than not they are reliable and they can help us understand general characteristics of the population we're interested in. When we have representative samples, we can be reasonably confident that our conclusions will in fact transfer to the broader population. We have one last important point to make before we close this video. That's to understand something called statistical significance. So again, I'm not going to ask you to do any math here, but I do want us to walk through that conceptually. You may have heard this term statistical significance before when hearing about the results of a study summarized. So what does it mean? Simply put, a statistically significant result is one that is unlikely to have occurred simply by chance. More specifically, researchers calculate something called a p-value, which is the probability that a distribution of scores at least this extreme would be observed simply due to random factors. The lower the p-value, the less likely the result is due to chance alone. By convention, the traditional cutoff for significance is p less than 0.05, which is less than a 5% probability that our results are simply due to chance. As an example, let's say we have a hypothesis that consuming caffeine improves memory. We could design a test for this by creating two groups. One group of participants who drink a caffeinated beverage and another group who drinks a similar but decaf beverage. And then we could have them complete a memory test. We can now look at the results and see if they are consistent with our hypothesis. Let's say that the caffeinated group answers 12 out of 15 memory questions correctly on average, while the decaf group answers only 10 out of 15. The caffeinated group did better, but only slightly. Is this enough to say that caffeine boosts memory? Or were the results simply a fluke? To answer that question, we need to look not just at the overall means or average scores, but rather at the distribution of scores in each group. So let's see more what that might look like. First, let's imagine that we have the following set of results. Here we can see two distributions, one for our caffeine group on the right and the other for our decaf group on the left. Even though the caffeine group only boosted scores by about 2 points on average, you can see that the two distributions are completely non-overlapping. That is, everybody in the caffeine group did better than everybody else in the decaf group. That's a pretty extreme result that's unlikely to be due to chance. A statistical test comparing these two groups would likely yield a very low p-value. So just for example's sake, let's say that we obtain a p-value here of 0.003. That means that there is less than a 0.3% probability that these results are simply due to chance. That's much less than the cutoff of 5%, or p less than 0.05, so these results would be considered statistically significant. In other words, we can have some confidence that this is in fact a real effect and not simply a fluke. More often though, our data looks something like this. Here we still have two distributions, and the means or average scores are still pretty close to the same as before. That is, the caffeine group still scores about 12 right on average, compared to only about 10 for the decaf group. Notice though that now there's much more overlap between the two distribution of scores. Many participants who consumed caffeine still didn't do that great on the memory test, and many who were in the decaf group still did pretty well. The caffeine group still did score higher on average. However, now when we look at the distributions, it's less clear if this is truly a real difference or if this is just due to chance. And to find out, that's why we need to run a statistical test and calculate a p-value. So again, just for example's sake, let's imagine that after running a test on these data, we obtain a p-value of 0.16. That's higher than the 0.05 cutoff, so that would be a non-statistically significant difference. So simply based on these data, we would not have sufficient evidence to conclude that caffeine influences memory. The procedure we just went through is called null hypothesis significance testing. That's quite a mouthful, so sometimes we just abbreviate it as NHST. We start with a null hypothesis, the assumption that there really is no meaningful effect or relationship. And we then compare our data with that null hypothesis. How likely is it that we would have gotten the data we did if the null hypothesis were true? If we get a low enough p-value, that is less than 0.05, then we can reject the null hypothesis and conclude that there probably is a real effect, a real relationship. If, on the other hand, we obtain a p-value higher than 0.05, we would fail to reject the null hypothesis and therefore fail to find evidence of a real or meaningful effect or relationship. NHST is not perfect, and there have been several critiques of it over the years. However, it is currently the standard we use not just in psychology, but in other scientific disciplines as well. So next time you hear about a study that found a significant relationship or significant effect, you'll know a little bit more what that means. In this module, we covered the basics of descriptive and inferential statistics. For the exam, you should be able to describe the difference between descriptive and inferential statistics, describe a normal curve, and explain the meaning of statistical significance and interpret a p-value.